Good morning, afternoon, and evening, everyone, and welcome back to Fike's spring/summer series of webinars regarding combustible dust. We are extremely happy that you're with us today. The topic of today's webinar is combustible dust risk and reduction methods. My name is Carson Stevens, and I am the Explosion Protection Business Development Manager for the Pacific Northwest and also for our OEM partners. I, along with two other experts in the field, will be speaking with you today regarding explosion prevention, as well as some passive and active methods of explosion mitigation. First, we're going to hit the prevention, and with us today is a good friend of mine, Dr. Nick Redding, Fike's US-based explosion protection scientist. Good morning, Nick, and the floor is yours, my man.
Thank you, Carson, for the introduction, and thank you all for finding the time to join us this morning. The first topic we have for you today, like Carson mentioned, is to kick off the series on risk reduction methods, and this topic initially will be explosion prevention methods. The first step toward performing a proper process hazard analysis is to identify the hazard and quantify the risk that might be involved. For those of you who may not be as familiar with these terms, generally speaking, a hazard is the potential of a machine, equipment, process, material, or physical factor in the working environment to cause harm to people, environment, assets, or production. And risk is the possibility of injury, loss, or environmental incident created by that hazard. The significance of risk is usually a function of probability or the likelihood that a hazard might be present, and the severity or the consequence of that hazard if it's likely to proceed. An operations team's overarching goal is typically to maintain adequate prevention mechanisms such that the likelihood of explosion events is minimized, leading to a lower overall risk. So first, like I had mentioned, we want to identify and characterize the hazard that might be involved in your process. The hazard, as far as Fike might be concerned, would be a dust plus the atmosphere that it is involved in, as well as the activities that take place around the operations where the dust might exist. As far as combustible dusts are concerned, you can see a variety of materials that might be involved in these types of explosion incidents. Largely, you'll see food and wood processing hazards, but following closely to that are metal dust hazards, plastic dust hazards, and then you'll also see trace amounts of coal or other types of inorganic materials. A few global questions one might be able to ask to better understand and characterize their hazard might be: what processes, equipment, and work areas are at risk? What are the fuels, oxidants, ignition sources, and operating conditions involved? And then finally, what are the characteristics of the hazardous fuel that is present? And has there been any explosibility or combustion testing done for that particular hazard? A little bit of background for you about combustion dynamics before we jump into the meat of prevention. So you need 5 things for a dust explosion to occur. We call this the explosion pentagon. First, you need a dust or a fuel that is combustible. The dust that is present needs to be capable of lofted dispersion. You need to be able to put that dust into suspension within your environment. You also need an ignition source of sufficient energy able to ignite that deflagration. You also need an atmosphere that contains sufficient oxygen to sustain propagation of that flame. And then finally, you need confinement of that dust-air mixture within an enclosed environment. That is usually what is able to generate the pressure effects associated with an explosion type event. And if you remove any one of these elements, that could be enough to prevent a combustible dust incident from occurring at all. But it is important to note that prevention measures, although they do reduce the risk of an incident taking place, they cannot completely eliminate that risk. And for that reason, dust explosion protection or mitigation systems might still be required. So now moving on a little bit more specifically to explosion prevention, 2 of the most common opportunities for prevention are 1, the control of ignition sources, and 2, the reduction of the existence of explosible dust clouds. So for ignition sources, we can do a variety of different things. We can control the temperature, we can issue more restrictive hot work permits, we can have grounding, bonding of our equipment, magnetic screening to capture loose parts that might be flowing through your process unseen, and then hazardous area classifications as well. For controlling the existence of an explosible dust cloud, we can inert with nitrogen, carbon dioxide, argon, or other rare gases. We can inert by adding inert powder material like a rock dust or sodium bicarbonate. We can monitor the dust concentration or the oxygen content. And then we can practice good housekeeping like cleaning or dust removal through pneumatic nuveyance of nuisance dust that might be surrounding areas of your plant or equipment. There are a few other ways we can do that as well. For prevention as a whole, we can divide our workplace into certain zones based on the type of hazard that might exist. We can select suitable equipment to do the job, and we can de-energize that equipment to prevent an explosive or potentially harmful atmosphere from being present. For ignition prevention, this is usually one of the easier tasks that a plant can take on to prevent an explosion from occurring, is controlling that ignition source. So it's important to both recognize where that ignition source might occur and then design an adequate solution for both the detection and control of that ignition source. It's important to both verify that the solution will be valid and that it will be both valid, verifiable, and efficient as well. You can usually classify ignition sources in two different ways: trivial ignition, like unauthorized smoking, welding, or cutting, which can be managed by good management processes and proper process safety protocols. And then alternatively, there are ignition sources that are inherent to the process, which can typically be managed by use of dust ignition proof or explosion proof equipment. Here is a good tabulation that we have procured from a BIA report. It covers over 600 explosion incidents, and it tells you what the most likely case of ignition might be. Largely, the industry tends to see ignition using or due to mechanical friction. Second, we see it quite often with smoldering, static electricity, and friction. There are a few others here. We'll go through these a little bit more specifically in the slides to come. The first one I did want to talk about was heat from mechanical parts. So you can typically see this in two different ways: flying fragments from solid materials or hotspots where equipment might be impacting repeatedly during your process. So solutions to solving this issue from an ignition control standpoint. So we would potentially think towards pneumatic or magnetic separation of those foreign bodies that might create those impacts. Other good engineering practices for this might be removal of those foreign bodies from the process stream using that magnetic or pneumatic separation method. We can avoid construction materials that can induce incendiary metal sparks or thermite flashes. And then finally, we can also inspect the process frequently and remove any causes of impact immediately whenever they're seen within your process. Usually if you hear an unusual noise that an operator might not be familiar with, that could indicate that there is some unnecessary impact taking place. Next ignition source I did want to talk about was electrostatic discharge. This can be from a charged human or an operator. It can also be a spark between a dust cloud and a conductive container. Recommendations to reduce this type of risk would be to use a conductive or a low dielectric strength material for your equipment. It could also be to ground all conductive parts of that equipment that might end up becoming charged. You can ground personnel if the low minimum ignition energy dusts are handled. And then finally, you can ground electrically conductive materials like metals using grounded conductive equipment without non-conductive coatings. We did mention minimum ignition energy on the previous slide, so I did want to cover that in a little bit more detail. We call it the MIE. It covers the sensitivity that a particular dust fuel might have to ignition. MIEs can be 500 millijoules or greater, meaning that they have a very low sensitivity to ignition. In cases like this, with a high MIE, grounding the plant and equipment would be normally sufficient. The lower MIE you have, 10 millijoules, lower, even 1 millijoule, we'd call that highly sensitive ignition or extremely sensitive. In these cases, you might want to consider restrictions on the use of highly sensitive non-conductors. Ignition energy as a whole is typically a function of dust size, size distribution, concentration, and local turbulence, so it's important to characterize this for any type of hazard that you might be processing. Another ignition source and potential opportunity for ignition control is the existence of open flames and hot gases. We can avoid these by enforcing adequate organizational procedures and routines. Prohibition of smoking in areas where combustible dust exists is an example of that. We can also enforce or firm guidelines for performing hot work. An example where this might become an issue is gas cutting torches. They become particularly hazardous because they function with oxygen in excess, which increases ignition sensitivity and risk of primary explosion development where explosions in air would normally be unlikely. We can also have hot gaseous products as well. So if you think about much like how air becomes pulled into a smoke plume above a fire, hot gas products may entrain into combustible dust areas, which increases the mixture's tendency to reach its auto-ignition temperature, and it could lead to more spontaneous initiation of explosion events. Another ignition opportunity is through self-heating and smoldering. So self-heating in a powder and a dust deposit is usually dependent on the dust characteristics, the surrounding atmospheric temperature, and the size of the material pile. But it is key to note that the potential for self-heating should be discreetly evaluated for your particular hazard during your hazard identification process up front. A couple key aspects that we can point out to prevent the influence of smoldering. One would be the control of temperature, moisture, and dust properties before you're admitting that dust to storage within certain operations like silos. Another thing that we can do is ensure that heated solid bodies don't become embedded in the bulk powder that's contained or stored. Monitoring the possible development of gaseous decomposition and oxidation products for early detection of self-heating is also important. This includes continuous monitoring of carbon monoxide concentration in air, which is it's a secondary combustion product, and we can also monitor the temperature at several locations within that product pile. We can also think to influence operations so that they reduce the residence time for gradual smoldering by rolling bulk material from one location to another frequently. And then finally, we can inert that bulk material in a silo by use of inert gas like nitrogen, argon, or another rare gas. Another ignition source here that I have for you is hot surfaces. So these can occur in plants intentionally and unintentionally. They can occur on external surfaces of hot process equipment or electrical equipment. They can occur within blowers, fans, mechanical conveyors. They can exist as overheated bearings or due to the impact of misaligned moving metal parts. When the temperature of that hot spot exceeds the minimum ignition temperature of the dust layer, which is a property of the fuel, that dust accumulation could start to smolder and burn, which ends up leading to the development of a fire situation. When a combustible dust cloud comes into contact with that smoldering or burning dust layer, that's what can lead to a more lofted dust explosion event in the form of an open air deflagration or a contained deflagration, depending on where that might be occurring. So a few measures that we can take. We can remove all of that combustible dust in the surrounding area before performing that hot work. That's part of good housekeeping. We can prevent and remove any kind of dust accumulation on hot surfaces. We can use electric equipment that is approved for use in the presence of that particular type of hazard or classification of hazard. We can inspect and keep good maintenance on procedures that might minimize the risk of overheating. And then finally, we can use temperature sensors to stop the process in the case of any hot surfaces or overheating that might go beyond the norm of that process allowance. And I think this is the last ignition source that we want to cover with you guys today. It's sparks and embers. So in general, sparks and embers are generated due to normal or malfunctioning product process. This can be due to misaligned or colliding moving metal parts, overheating in dryers, self-heating, A spark typically exceeds the combustible dust minimum ignition energy, which is not great. That can lead to ignition and continued deflagration. And then finally, sparks are conveyed through pneumatic conveyance lines and create fires and dust explosion events downstream within other equipment that you might consider protected, but the spark is being allowed to propagate from one unit to the other. So that's it on explosion prevention. I hope you took a lot away from that. Up next, and this being said, we left spark and embers. Now we want to talk a little bit more about high performance spark extinguishing. And my friend Giannis Langa is going to be speaking on that in a little bit more detail. If you have any questions on explosion prevention as a technique, please feel free to reach out to me directly.
Before we move on, I just want to interject one thing. At the top of the webinar, I forgot to mention that we're doing a little bit of a Q&A at the very end of the presentation. So if you have any questions in the meantime, while you can think of something, put them in the chat. Otherwise, and we'll get to those at the very end. But thanks, Nick. I liked the hazard risk analogy. I liked that a lot. It reminded me of this this meme that I saw out there for like a taco, like they had ingredients for a taco, and then the tacos were assembled, somebody was eating, and it reminded me of like a taco hazard versus a taco risk. Anyway, but anyway, so like Nick said, Giannis is going to come up. He's going to talk about explosion, or he's going to talk about spark extinguishing systems. And he is the account manager for T&B Electronic in Europe. And thanks for joining us, Giannis, and good afternoon to you.
Thank you very much. So let's speak a little bit about the spark extinguishing systems. First, let's talk a little bit about the risk. What is the risk we are talking about? During the processing and separation of materials, sparks and embers can occur, and together with flammable dust, chips, wood, chips, flakes, it can cause fires or even explosions. So what is the goal of the protection? We want to reduce the risk of ignition sources entering endangered parts of our plant. For example, there are filters, silos, cyclones. So what are we using for it? We will install spark extinguishing systems. And in conjunction with material discharge path or shutdown of the production line, we can significantly minimize the risk of a total loss of the plant. Here's a small table about applications. We see spark extinguishing systems. For example, some protection objects we see are filters, silos, bunkers, for sure dryers, mills as well, pellet presses, and other things for sure. And the industries are very different. There are many industries. Just for example, the wood industry, food industry, chemical, recycling, automotive, and for sure many else. Here you can see a typical installation of a spark extinguishing system in a suction pipe. Into the suction pipe, you can see some detectors here. If an ignition source is flying through this suction pipe, the spark detectors will see them, and they detect the radiation, the infrared radiation of the ignition particle, and within milliseconds, an automatic extinguisher, which is installed in the suction pipe as well, will extinguish the ignition source with 5 bars. So if an spark or even an ember is detected here at the spark detectors, within 80 milliseconds we will create in water dust into the suction pipe, and the spark will be extinguished. And the spark detectors and the automatic extinguishers come together at a spark alarm unit. You can see over here with some pictures as well. And to create the pressure of 5 bar at the automatic extinguishers, we need a system called pressure booster system. Therefore, you need or we install a pump and pressure vessel you can see over here, and water storage as well. Let's talk about protection concept for filters. Here you see a typical filter with suction pipes and back air and an outlet of the filter. So we install spark detectors in every suction pipe, and we install automatic extinguishers in every suction pipe as well. For sure in front of the filters, because we want to prevent that an ignition particle enters the filter. In the back air of the filter, we install some detectors as well. It's a different detector. It's a different detector. We will call about it a few slides later. We need those detectors in the back air as well, because we can see or we can detect smoldering fires into the filters very fast in the back air. In part, which is also important, is for example the outlet of the filter with spark detectors and automatic extinguishers as well, because sometimes the outlet of the filter there is a transport line to the silo, and if a spark enters the silo, for sure it's a very dangerous thing, so we shouldn't forget it. In addition, we can also install thermal detectors in the filter as well, or CO detectors. The thermal detectors is a good way to detect fires to detect fires in the filter if the process isn't running, because the spark detectors will only see sparks if the production is running. We need an airflow there. Here I want to give you a short overview of some key facts. What is the critical ignition energy? It's less than 1 millijoule, and the speed of the material is up to 185 meters per second. To be honest, I've never seen any suction pipe with an airflow like this, so it won't be a problem. If we extinguish in spark into the suction pipe, there is 1 liters per second, and we will extinguish into the suction pipe for 5 seconds. So there will be 5 liters in one extinguishing shot. The reaction time between detection and extinguishing is going up from 80 milliseconds, and it depends on the diameter of the suction pipe. And it's regarding to the diameter of the suction pipe. And in general, we have no interruption of the production. That means we have a spark into the suction pipe, and we will automatically extinguish it. You get an alarm, but the process is running. If there are detected some more sparks within 20 seconds, we will shut down the plant or the machine immediately. And those alarm levels you can choose freely. So detection of critical ignition sources. As Mr. Redding already said, the lowest ignition energy is about 1 millijoule, and the ignition energy of combustible organic gas. Sorry, the ignition energy of combustible organic gas is about 10 millijoule up. And an VDS approved spark detector, can reliably detect ignition energies of 1 millijoule. And for those detectors, you should use silicon sensors, and that is recommended in NFPA guideline 654 and VDS 2518. On this foil, I will show you our different detectors and the different ignition sources. On the one hand, we have sparks. There we see a temperature about 700 degrees up to 2500 degrees, and the ignition of a spark, the energy of a spark is more than 10 millijoules. Then we have embers. Embers have a temperature of 250 degrees up to 750 degrees, and the energy is approximately about 10 millijoule. Last but not least, we have hot surfaces with a temperature of about 100 degrees. There we see an energy of 1 millijoule. So for those different ignition sources, you need different detectors for physical reasons. All of the detectors have different sensors at the front, and every sensor is made for a different radiation of an ignition source. So if we have a typical flying spark, we will use our FSK detector. If we have a typically ember, or if we want to detect typically embers, we choose the FST detector. A new detector we have in our program is the FSM detector. This detector combines the FSK detector and the FST detector. Last but not least, there is an FST LT detector. This detector is able to detect hot surfaces about 100 degrees. Now we get to the international guidelines. Just a few of them. On the one hand, we have the DIN EN 12779. Operating the production process without complying with these standards there can be legal consequences for the manager. The next guidelines are some FM data sheets and VDS guideline, the 2106, some NFPA guidelines, and the BGE 739. Operating the process without complying with these guidelines will risk your insurance cover if you have a fire in your company. As a short summary, I will tell you the function of the spark extinguishing system on one foil. So those spark detectors are installed in conveying lines and will detect very small amounts of infrared radiation. And if an infrared detector detects the radiation into the suction pipe, it will start the automatic extinguishing. And then a small amount of the extinguishing mist will be injected into the conveying line. And in that moment, so your production process will be continue running, because the spark was detected, the spark was extinguished, and there won't be a problem. But if there are repetitive sparks, for example, 4 sparks in 20 seconds, the spark extinguishing system will shut down the process immediately, because you have to look at the machine if there is something going wrong, or is there many heat at the machine. You just have to take a look at it to be sure everything is fine. So what are the benefits of a Fike spark detection? On the one hand, we can detect hot sparks as well as burning embers and hot surfaces for sure. And we have proven field installations 30,000. Many insurance companies will know Fike and TNB, and every system comes with the Fike field service, what means commissioning and maintenance. Yeah, thank you very much for my short presentation. I will give my give my word to Carsten now. And thank you very much.
Thanks, Yanis. I know that was lightning fast. Thank you for that concise overview. It was a really fast time slot. So the next presenter is me. Let me make sure that I've got the right one up here. Okay. Wearing a couple hats, just want to make sure. Okay. The next, so let's say that prevention methods aren't enough to mitigate the full risk of the combustible dust hazard. You can see I've got Johnny Knoxville over here on the left. You know, he's doing his stunt on that TV show, and he's got his helmet on, but he's on a rocket. So I don't know if the helmet's going to help as much, but he's preventing some injury. But so you may not be able to fully limit the full risk of the explosion or fire, and there are other methods of mitigation that can help reduce the risk further. Some of the prevention methods we kind of talked about could potentially help with downtime, but maybe they're not as easily implementable. Maybe it's a really difficult process to perform housekeeping on. Maybe it's like a very old facility that requires a lot of maintenance to get it up to being dust tight piping and things like that. Or perhaps maybe this is a legacy product or a legacy process that it's been in service for years, gets a spark every now and then. We've never had anything before. Well, that's great that you haven't had a catastrophic event, but that doesn't necessarily take the risk away, especially in the atmosphere we're in now. So what are some methods that we could control the explosion? And so there's an iterative process that every process engineer goes through, or every design engineer goes through with risk mitigation. And that being, they start at more passive solutions and move toward the active, adding different layers of protection to each way to reduce the risk further. So here's a really great representation of, and it's a flow map of what it looks like. And every single time that there's a risk available, or there's a risk to be protected against, this flow diagram is implemented. So you can kind of see it starts at the top left and moves down. Is it combustible? Can it be released to atmosphere? Is your enclosure outdoors? Can we use a discharge duct? I'll get into that in a little bit. Do we need to go flameless venting? Is that not feasible? Do we need to go suppression? Is there interconnected ducts? There always is on interconnected equipment, but that's kind of the progression. It's not just you throw venting at it and call it good, or throw suppression on it and you call it good. There's an iterative process to get there. My piece, I'll be touching on the passive side. Nick will do the active in a sec. So I edited this video and I'm going to show it to you. And what's going on is, this is a dust collector with unmitigated dust explosion hazard. We put it out in the middle of this field, out in the middle of Kansas, put a coal dust explosible cloud in it, put an igniter in it, a really small, let's say a small spark igniter, and it goes boom. What I found out was that GoToWebinar doesn't support video with audio, but just imagine Red Hot Chili Peppers being behind this while it's exploding, the whole thing. Just imagine it going, okay, so this is slow-mo, so this is Red Hot Chili Peppers. It goes like, ah, it goes like that. But anyway, you can see the dust go into the dust collector. Here it goes, and it's unmitigated. It balloons out, deforms. Here comes the fireball. Here's a secondary explosion coming out the top for unoxidized fuel, and it's just a massive plume right underneath it. That's why explosion venting is required, or some form of explosion protection. So that's the hazard. Here's what you can do to mitigate the hazard. Passive explosion protection would create a planned pathway. So think of it as a pressure relief device. Additionally, that doesn't necessarily stop secondary explosions. You can kind of see what this is going on in this is at our remote test site. These have interconnected ducts. The majority of process vessels do. Probably 99.9% of them do. But this has a planned pathway for the explosion directed outside. You can see there's some grass out here. It's going to a safe area, and there's interconnected equipment, and there's another video later that you'll see. But that's what's going on. Also, you can signal the occurrence of the event. So there's different indicators that say, hey, there's an explosion. We need to stop the fan from feeding the explosion fuel, so you don't have secondary fires and explosion. The how. We do it with explosion venting and explosion isolation first. That's the first line of defense, and I talked about that a little bit earlier. But explosion venting is accomplished with either we call it free venting. That's what code calls it, free venting, and that's just explosion vent panels that are on your enclosure. If it's inside, the next step would be to do a deflagration discharge duct, and that's just a duct that directs the explosion out the building. More on that in a second. And then flameless venting, that's this big red thing that you see over here. That bolts right on top of an explosion vent and suppresses the fireball that you saw underneath that big coal explosion. It suppresses the whole thing with a stainless steel mesh, and it releases the gases. Additionally, there's explosion isolation that's required to keep the explosion in the one risk area. You don't want it to be propagating back upstream, consuming a bunch of fuel, or you break a bag or something in a filter and it goes down the clean side, and now you're directing fireballs towards people at process equipment and what have you. Here's a video of the anatomy of an explosion vent. It's really not that complicated, but you bolt it to the side of your enclosure. Here comes the spark on the inlet of the enclosure. It ignites the dust cloud that's in it, because you have air pulse, you have dust layers and things, and it opens in various score patterns, but it opens to a safe area. It doesn't balloon, it doesn't deform the vessel, there's another picture of one. It doesn't create more or less a big bomb to where it could have shrapnel or fireball and injure people. It directs it to a safe area. This is a video of a remote test site. Again, it doesn't have audio, so I'm going to talk through it with you. So here's what's going on. So this is at our remote test site. We had a demo day for a group of students and some faculty of some universities around. This is a vent cube demonstration. You can kind of see what's going on. I'm going to stop it. So we're igniting it. We're igniting the dust cloud that's in this. Here comes the explosion, and it's coming all the way out this way. Now the people aren't standing in front of it. Please know that we wouldn't do that to people and scare people like that, but it comes all the way out. There's people over here. The fireball's directed this way. Watch these people are anticipating this explosion venting demonstration to happen. They're anticipating it. So watch them all jump whenever it happens. See them all jump down here? They knew that was coming. Look how big of a vent cube this is. This is small comparative to what we see out in the field or what other people have, vendors. And there's people jumping back there. You can see people jumping at the very end of it, at the end, because it was like, woo! That got some people's attention. See, there's some people jumping back here, stuff like that. So that is free venting. You would not want that to be directed inside of a building. This is outside, safe area. We know it's coming. Imagine not knowing it's coming and that being inside. Let me get to the anatomy of how the explosion venting, how that free venting situation, or what transpired during that. Quickly, this is our coveted pressure versus time curve. We love this curve. It has a great demonstration of what. So follow my mouse here. So stagnant atmospheric pressure. You have an ignition. You have a dust cloud present. Here goes the deflagration. It's increasing. That P-act is actually the P-stat. So pretend that's P-stat. That's the burst pressure of the vent. The vent bursts. It starts relieving the pressure. It still has a small increase in pressure all the way up until it gets to the P-red, then comes back down to a normal pressure. So that's kind of what those names are. P-stat, P-red, if you see those. The P-red is the maximum pressure you would see in a deflagration event versus a P-stat, which is the burst pressure. It's rising, it's falling. Here's your ignition source. Vent ducting. Vent ducting is, I'll be fast here, but there's an explosion vent, you have the enclosure indoors, and you need to go up and out the building with the explosion, or maybe out the side. that it has the ability, although whenever you start calculating for that vent discharge duct, you have to decrease the efficiency of it because it doesn't allow for free venting of the explosion event. We normally say that it's within an arm's wingspan. If you can touch an exterior wall in an enclosure, you can probably get it to work. But if let's say you're in the middle of the room, a 50-foot long explosion vent duct is not going to be acceptable. Here's a flameless venting demonstration. So this is an event that goes over the top of an explosion vent and suppresses the fireball. If you can tell, it's much less exciting. There's not a fireball. You can see all these people. There it goes. Nobody jumps. It's suppressed. The noise is suppressed. It goes through the stainless steel mesh, suppresses the fireball, and it's done. There's no need for an explosion vent duct or free venting. You can put that indoors anywhere. That's the advantage of flameless venting. So that's all for the deflagration side. That doesn't handle interconnected ducts. So the solution for interconnected ducts is a passive isolation device. Here's an example of our DFI. But what it does is the pressure wave, the deflagration pressure wave, will slam a valve or gates or flaps shut, and it isolates the explosion from traveling further in through the interconnected ducts to an unprotected vessel, let's say. Here's a quick demonstration. This is at our remote test site. This is cool because you can see Lexan pipe. So here's the dust being conveyed into the enclosure. You can see it's still moving. It's still moving. And then it ignites. And then when it ignites, it travels back upstream. And this explosion isolation valve is slammed shut. Here comes the pressure wave. Boom. It's slammed shut. You can see it there. And you can also see that's not the video. That's pressure oscillations trying to jam it open, pull it back open. So it locks in place. This can be put vertically. It can be put however many bins you want. You can put it in there. And look, and it's isolated the explosion. Here's all that fuel just sitting over here, not ignited. That's how you know it works. Pretty cool. Here's a real time. This is a loud video. You're not going to hear any of the audio though, but here it is. So this is a 32-inch DFI, diameter DFI, and what's happening is here's the enclosure where the deflagration occurs. It travels back upstream. This is all unburnt fuel. Here comes the fireball. It goes back up the stream. It isolates it. Here's how you know it isolates it. It's actually this way. It's faster. So right here, you can see here's the explosion, here's the isolation valve, here's an open pipe and a fan pushing against it. Nothing. It's isolated. So there's not always a scenario where you can fit explosion venting within this. So there's some cases where there's a weird geometry or you can't discharge dust, in which case that goes for more of an active isolation or active suppression thing. So quick sum, the benefits is these are more cost effective. You can install them yourself. They're easy to maintain. You can maintain them yourself. There can be a lot of application flexibility. You can put them vertically, there's bins and what have you. And normally it's faster and expedited lead times because there's less engineering involved. So with that, that's the passive isolation. And now, let's say you can't do passive isolation. You've got an enclosure right in the middle of the room, and you need to do something else. We've exhausted all of the other avenues. Now it's time to look at active explosion suppression. And for that, I'm going to turn it back over to Dr. Nick Redding. Nick?
Thank you, Carson. If everyone can see my screen, I hope you can. As Carson mentioned, he gave us a good insight into active or passive explosion protection methods. I'm going to be covering the active portion of that. The only difference here being that now we're going to have detection, which initiates response and control systems, which initiates a further activation of our protection system. So no longer passive, pneumatically activated or activated based on a pressure front, but now we're actively controlled. So first, I do want to cover a bit of a stepwise approach towards the hazard and the initiation of a deflagration. So let's say you've got an ember, a spark, or an alternate ignition source within your primary combustion vessel, and it interacts with a combustible dust that's that's in suspension and confinement. So once that ignition hits that combustible dust cloud, you're going to have the initiation of a deflagration event that's going to be quickly expanding both the pressure front and the flame front until it hits the vessel wall. And then pressure will be then generated at that point until we exceed the maximum allowable working pressure of the vessel that the origination occurred in. That enclosure will then begin to deform and explode as it hits detonation velocities. The vessel parts, flame, and blast waves get ejected, which can damage nearby process operations, and they can create hazards for operating personnel that might be in the surrounding area. The ejected pressure wave and flames can stir up and ignite dust that has accumulated on surrounding environments, leading to secondary explosion events that can be more significant than the original event that occurred within the primary vessel. This flame and pressure can also propagate down interconnected pipework, like how Carson touched on, leading to events occurring within conveyors or downstream equipment, whether that be upstream or downstream. Flame can propagate in either direction. So how do we tackle this kind of issue? So actively, there are three main ideas that we can lean on as our principal functions. One is suppression or the extinguishment of the primary deflagration. Another is isolation of that explosion to prevent propagation of flame and pressure to other interconnected areas upstream and downstream. And finally, we can signal the occurrence of that explosion event within the customer's PLC, just to trigger other alarm and response units that might be needed. The active explosion protection solution is able to mitigate the effects of a deflagration so that we minimize the hazard level and the severity of that hazard. We can guarantee no equipment damage within that primary location. And then we can also limit the ejection of flame and harmful blast waves during propagation within that vessel and to other interconnected locations. So the solution in a little bit more detail from detection to activation and response of our system. First, you have pressure and flame or infrared detectors that are continuously monitoring the enclosure or the space where the hazard is known to exist. When there is a sudden change in that pressure threshold or infrared level, the controller will initiate activation of the explosion suppression and any adjacent isolation devices. The explosion protection control system then signals the process control system to shut down all equipment, preventing any kind of further hazard or damage in other interconnected zones. And then after the reset and refurbishment, which is our word for the replacement of suppressant and actuators that allow for initiation of our devices, the production process can be quickly resumed. So a little bit more detail about the devices that are involved in an active system. First, you have your explosion detection and your control. That leads to a control panel being needed for a particular solution. We also have detectors, like I mentioned, both pressure and optical or infrared detection. For the suppression protection, we typically utilize a high rate discharge container or an HRD container. That's shown here on both the silo primary volume and on that dust collector primary volume. And then for explosion isolation, we can do a few different approaches here. We have standard rate discharge containers, which is a chemical solution to isolation. We also have mechanical solutions to isolation, whether that be a gate valve or a pinch valve. A little bit of detail more on suppression as a protection solution first. So after we activate our system through detection and input signal to our controller, the HRD suppression container will inject a certain payload of suppressant agent into the combustion volume, what we consider to be the protected volume. That suppressant agent engulfs the deflagration, chemically extinguishes the combustion reaction, absorbs a lot of heat away from that combustion chain reaction, and prevents pressure increase beyond a certain predetermined design limit. The suppressant powder will also extinguish any fires resulting from the explosion event, and it will remain airborne, creating an inert powder environment to create any kind of continued or sustained combustion after the initial primary event has occurred. A little bit of a timeline here from a pressure versus time perspective. Carson gave you this profile already for venting. It's very, very similar for suppression. We're going to have ignition. Once we have ignition of fuel, that pressure begins to rise. Once that pressure hits an activation level that's set by the design, it triggers our suppressant container, our HRD container, to inject that payload of agent within the combustion volume. Once it fully intermixes, we see that pressure start to curve. Once it curves off at a total suppressed pressure, or a TSP value that is predetermined by the design, the pressure starts to subside as the deflagration becomes mitigated and extinguished. The goal in our system is to design that TSP so that it's larger than the activation level, obviously, but lower than the equipment design strength, so that no equipment damage occurs. Now we'll switch gears from suppression with HRD containers to chemical isolation with SRD containers, or standard rate discharge containers. So again, after your detection and activation of your system using controls, that SRD container injects a certain quantity of suppressant agent into the interconnected duct, pipe, or conveyor. This isolation location will be at a specific distance so that it's quick enough to stop flame before arriving, but not too far to where it injects its full payload before flame even arrives at that point. It creates an inert barrier between the source of the primary deflagration and any adjacent connected equipment that we want to keep within our protected area. The inert barrier extinguishes flame that would otherwise propagate to those other protected units, thus eliminating the risk of any kind of secondary explosion events. Process interconnects with internal moving parts such as screw conveyors, belt conveyors, elevator legs. These can all be activated using chemical barriers. You can imagine if there are moving parts within that pipe, like as in for a conveyor or a bucket elevator, there are obviously buckets. You would not be able to implement an active mechanical isolation solution there with a valve. That would be a scenario where chemical isolation would be the preferred isolation method. A little bit of a video here for you on chemical isolation. We have a little bit of the same issue as before. You might not get any audio, but I will talk through it for you. We'll see how quickly this plays. I'll play it one more time because I don't think that was slow motion, and I don't think we have that slow-mo file for this particular test setup, but I'll play it one more time and talk through it. So you see out the top, you have flame front being relieved through relief venting, a passive device like Carson showed you before. On that ductwork that you see there in the center of the video, you do have a SRD chemical isolation container, and you notice that there is no flame escaping out the open end of that pipe. All you see is a large quantity of inert material, our agent, sodium bicarbonate. So now we'll talk a little bit about mechanical isolation as a solution for isolation. We discussed suppression first with HRDs, then we talked about chemical isolation with SRDs. Now we'll talk about mechanical isolation. You can get away with that with either a gate valve or a pinch valve to create that mechanical barrier between the primary ignition location and any kind of adjacent equipment that you're trying to keep within your protected zone. The mechanical barrier stops both flame and pressure. So it's a little bit different from chemical, which only stops flame but not pressure from propagating. Mechanical barrier will stop both flame and pressure, which can save upstream and downstream equipment from any type of additional blast wave damage. So when do we require active protection? In general, it would be required when explosion venting to a safe location or flameless venting is not possible. We also want to prevent the release of hazardous products if they're toxic to personnel or to the environment. So in that case, relieving all of those products through venting would not be suggestible. We'd want to go with more of a suppression approach, keep all of that combustion and toxic byproducts contained within the primary vessel. We would also go towards active if the equipment does not have enough available surface area to support the amount of vent panels that might be needed. Depending on the hazard, if there's a high KST, obviously you can imagine you need more relief area to keep moderate reduced pressures within that enclosure. If you can't have enough real estate to keep all those vents in place, suppression would be your next alternative. And then finally, if you need a fast resume of your production process after the explosion event, suppression is typically quicker for rebuild and reload. Other areas where you might think towards active, so you can expect that there wouldn't be a passive solution if your explosibility characteristics or design criteria are too high, and if PA68 has limitations on how you can design for free venting. If you're outside of those limitations, suppression might be the next alternative. You can imagine also that the duct size might exceed the passive explosion isolation valve sizing that exists. Flat valves are only available within certain size ranges and up to a certain size. So if that occurs in your process, maybe it's a 100-inch duct, there won't be a gate valve or a passive valve that can support that type of size. Chemical isolation might be a better solution there. And then also duct geometry. So if it's a rectangular duct, that doesn't bode well for a passive system, but chemical isolation can be a solution there as well. Explosion protection systems are also needed to protect against spark propagation. That is usually a passive system is not going to save you for spark detection, but as Giannis had mentioned, active systems can be more our friend for any kind of spark propagation and extinguishment. We might also need an active system when we have an ingress of oxygen into the process after an event, and we need to prevent the risk of any post-explosion fires. Remember, during HRD suppression, we inject a lot of agent inert material, and that creates an inert atmosphere, which prevents any post-explosion fires. Other benefits, from an electronic standpoint, we can provide supervision of safety, health, and trouble indication during the course of the event. And we can also use this to optimize the design as it currently stands. We can store all of that information and display the detector readings and system events real time. It's easily integrated into process controls and allows for visualization systems to be integrated as well. It has a smaller footprint than a lot of explosion vent panels do and a lot of passive isolation systems, and we consider it to be non-intrusive to your process. It doesn't produce material that would induce a lot of product buildup or any kind of pressure drops within your system. And finally, a few additional benefits relative to passive. We do have to keep in mind that with active systems usually allow for the immediate extinguishment of an initial deflagration. It clogs that deflagration momentum from developing any further momentum, whereas a passive system allows it to run its course. So a little bit different strategy there. Active systems allow for low risk for flame propagation down interconnected ducts. They have an equivalently low risk for post-explosion fires, and they induce situations for minimal equipment damage, fast reset or reload of your system, and which then equates to a prompt resume of any kind of production or operations, reducing the overall amount of downtime that you might see. And I think that's it on active protection for us and isolation. If there are any questions, I think Carson will take over now to field some of the questions that you guys might have.
Thanks, Nick. Okay, so we've got 2 minutes left in our presentation. I'm gonna try to get 2 questions in. There's a lot of questions. And again, after the webinar, we'll take these offline. We'll send them responses along with, no fear, there will be video of this webinar, a presentation, as well as all 3 of the previous presentations as well, all available on fike.com. We're working out the landing pages right now, but they will be at your disposal soon. So first question is for Giannis. What sort of maintenance is required for a spark suppression system, Giannis? And we have 1 minute, so fast.
So what maintenance is needed? We need to check if the optics of the spark detectors are broken. We need to check if the machine shutdown is working, and we have to check if the nozzles of the automatic extinguishers, if they are they broken or are they okay? Those are just some parts we have to check in the maintenance.
Got it. Thank you, sir. And then Nick, one quick one for you. What happens when an enclosure is designed for PMAX? What sort of isolation is required for something like that?
So something like containment?
Yes.
So yeah, if you're designing for containment, which is a great approach, you're basically designing that enclosure to exceed the worst case Pmax value of your fuel and explosibility property. In a case like that, I would look more towards mechanical isolation. Depending on the application, you might need chemical isolation as a supplement to that mechanical EIV valve. But mechanical isolation would be typically the solution that I would go straight towards for a contained vessel.
Awesome. Thank you guys. And thanks for everyone for joining us today. We really appreciate your attention and your time, and we look forward to seeing you next week. Again, look for Fike.com for the webinar. All right. Thanks, everybody. Have a great day.